Hello and welcome to this IB Maths Intense session, part of Topic 3, Geometry and Trigonometry. We're working with triangles. This is our second video on triangles. And this is an incredibly important topic, the unit circle. The unit circle here, looking at the unit circle in terms of angles in degrees. But this is essential knowledge for you as you get into more trigonometry, and especially when you get into measuring angles in radians and thinking about circular measurement. So it's essential that you can grasp this topic, and we'll start with looking at the topic in degrees, which we've seen before, and then at a later stage we'll introduce you to the idea of radians. This is something that's on the IB specification. We're expected to be able to define cosine and sine theta, and we'll look at tan theta as well in terms of the unit circle. So what is this unit circle and how does this work? So this will make your brain hurt a little bit, I think, but not to worry. Let's concentrate and see if we can master this very important topic. Here we've got a circle, and it's got a radius of 1. You can see there that the coordinates are 1, 1, 1, 1, minus 1, etc. The circle has a radius of 1. And I can mark any point on the circumference of that circle. I'll just mark this point here as P. It's got coordinates x, y, obviously. And you can see that it creates an angle with the x-axis here. Angle here, let's call that theta. Now, if I look at this radius that I've just constructed, OP, it also can be used to create a nice right-angled triangle, rather like we've seen before. And if I label the point there N, you can see we've got a nice right-angled triangle, OPN. Now, so what you're going to ask, what does that mean? That's not that interesting. But if we know that the coordinates of the circle at any point on that radius are x, y, let's have a look at that right-angled triangle, and it will tell us something about what x and y denote. If I look at that triangle, I can see that cos theta in this right-angled triangle is, well, we know the cosine is the adjacent side, that's ON in my triangle, divided by the hypotenuse. Cosine adjacent over hypotenuse. Well, the hypotenuse is equal to OP, but its value is 1, because the radius is always 1. And here, the length ON is the value of x. So cosine theta is actually equal to x. And sine theta, sine is opposite, which is Pn, over hypotenuse, which is OP. This time, the coordinates there tell me that that would be equal to y. So this remarkable unit circle, the coordinate Pxy, is actually the coordinate cos theta. My x value at any point on the circle is cos theta, and the y value is always sine theta. So whatever angle I make here for theta, if I go to the circumference of the circle, the coordinates at that point will give me my values of, well, x will give me my value of cos theta, and y will give me the value of sine theta. So if I was to move that red line to a number of different points, so for example, if I took the red line and put it right on the x-axis, there, all the way there, then, well, what would that tell me? At that point, my coordinate is 1, 0. So when the angle is 0, at theta equals 0, well, what have I got? Well, the x coordinate, which is cos theta, is equal to 1, and sine theta, which is the y coordinate, well, is equal to 0. And if I go to the other side, here, and put my hypotenuse, if you like, up the y-axis, so at theta equals, now I've created an angle of 90 degrees, then this time cos theta, my x-coordinate, is 0, and sine theta is equal to 1. And those are important values that we need to remember, and they come from that unit circle. If I take the example that we were working with in the earlier video of 45 degrees, so if theta is equal to 45 degrees, I've created an isosceles triangle. So my sides NP and ON are the same. So x is equal to y. So I know that my hypotenuse of 1 squared must have equaled the square root of x squared plus y squared. But x and y are the same, so 1 squared must have equaled 2 lots of x squared. And if I take the square root of both sides, that tells me that x, which is equal to y as well, must both be equal to 1 over root 2. So for the angle 45 degrees, at 45 degrees, sine 45 is equal to cosine 45, which are both equal to 1 over root 2. So you can see just within that single unit quarter circle of the first quarter there, which is measuring angles between 0 and 90 degrees by constructing this right angle triangle, anywhere along that circumference, the coordinates will tell us the values of cosine and sine. But of course, angles don't just live between 0 and 90 degrees. There are obtuse angles, there are bigger angles, and here in this example, I've created an angle now which is bigger than 90 degrees. Let's imagine that angle is 135 degrees. How do we use that to tell the values of cosine and sine? Well, one thing we know at the point P here, we know that our cosine of theta, or cosine of 135, well, the x-coordinate is negative now. So whatever angle we've got in there that's bigger than 90 degrees and less than 180 degrees, the cosine of that angle will be negative because our x-coordinate is negative. And sine theta, when the angle is between 90 and 180 degrees, is going to continue to be positive because the y-coordinate is still positive there. Now here's another thing. The triangle that's created here at the x-axis has an angle of 45 degrees because it will be the difference between 135 degrees and 180 degrees. And so we get a really nice result here that sine of 135 degrees is exactly the same value as the sine of 180 minus 135. In other words, sine 45. So we begin to construct a family of angles which have the same ratio. So sine 135 and sine 45 share the same value. Cosine of 135, it's going to have the same absolute value, but it's going to be negative this time. So cosine 135 is going to be negative cosine of 180 minus 135. So in other words, it's going to equal minus cosine of 45. And that's going to be very useful, again, with families of angles. They go together, but the signs change as we go round this unit circle. In general, we can generalize the result then that for angles between 90 degrees and 180 degrees, sine theta will be the same as sine 180 minus theta. And cosine theta will be sine change minus the cosine of 180 minus theta. So the example I've got there, for an angle of 135 degrees, sine of 135 degrees will be the same as sine of 180 minus 135. In other words, sine 45. And cosine of 135 will be equal to minus the cosine of 45. And I could do that for any angle. So if I change that value there, and it wasn't 135 anymore, let's say this is now 140 degrees. Well, the partner angle that goes with that is 40 degrees, because the two have to add up to 180. So sine of 140 would be the same as sine of 40. And cosine of 140 would be minus the cosine of 40. And that's how we handle angles between 90 and 180. But it doesn't just stop there. We can go now and look at any angle, any size, and a similar sort of pattern will emerge. If I construct an angle now that's in this third quadrant, let's imagine in general, we're going all the way around there. What we can say is in this quadrant that the cosine of theta, this angle theta, is going to be the x-coordinate. It's going to be negative. And sine theta in this quadrant is going to be the y-coordinate, and that's also negative. So in both of these cases, the ratio is going to return a negative value. And what's the partner that goes with that particular angle? Well, in the same as we did before, let's imagine that I create an angle that's between 180 and 270 degrees. So let's say it's an angle of 200 degrees in total. Well, the angle that's created here to construct this right-angled triangle is going to be 180. Well, 200 take away 180 is just going to be 20 degrees. So what do I know now? I know that the cosine of 200 degrees will be equal to the cosine of 100. It's going to be the cosine of 200 minus 180, which is equal to the cosine of 20 degrees. But it's going to be minus because in both cases, sine and cosine, in that quadrant, the ratio is negative. Sine 200 will be the minus sine of 200 minus 180, which is equal to minus sine of 20. So as a general rule for this particular quadrant, the third quadrant, my angle sine theta will give me the same value as minus the sine of theta minus 180. And cosine theta, similarly, will give me the same value as the minus cosine of theta minus 180. So let's imagine it wasn't 200 degrees anymore. Maybe, oops, didn't want to do that. Let's get rid of that completely. Say it's not 200 degrees. Let's imagine this is an angle of 250 degrees. Why not? 250 degrees. Well, 250 degrees is going to give me, so sine 250 would be the same as minus the sine of 250 minus 180 minus sine of 70, because the angle that I'm constructing here is 70. And cosine 250 would be equal to minus cosine of 70. The two are partners, their signs are just different. And what if I go into the fourth quadrant? Let's just get rid of those and let's construct something in the fourth quadrant, and let's see what happens with that. Well, anything in the fourth quadrant, let's draw ourselves a little line. We'll do that in black just so you can see that it's different. Let's construct something here. So this time I've got an angle that goes all the way round to here. That's going to be my theta. What I do know for, and that's constructing an angle also here with the x-axis. What I know about the x and y coordinates in this quadrant are that my cosine is going to return, because the x-coordinate is going to be positive, because my x-coordinate is positive, and sine theta, which is the y-coordinate, is going to be negative. So when an angle sits between 270 degrees and 360, then cosine is positive and sine is negative. And like before, an angle has a partner with a similar value. So let's imagine this was an angle of size 300 degrees. So cosine 300 degrees. Its partner is going to be, if this was 300 degrees all the way around to there, this angle here, the partner would be 60 degrees. So cosine 300 would be equal to the cosine of 360 minus 300, which is equal to the cosine of 60. Notice that the signs are the same because cosine is positive in both cases. Sine of 300 would be the minus sine of 360 minus 300, because sine is negative in that quadrant. So minus sine 60. So in general, where an angle sits between 270 and 360, we can say that cosine theta is equal to the cosine of 360 minus theta. And sine theta is minus the sine of 360 minus theta. It appears complicated, but once you get into the routine of working with angles and finding their partners, then you can find the values for any angle purely based on an angle between 0 and 90 degrees. You'll find its partner, and the only thing that might change is its sign. It might go positive or negative. What about angles over 360 degrees? There's no rule that says you can't have an angle of greater than that. So imagine that I constructed an angle here, but I'd actually gone round here once, 360 degrees, and then again to there to create an angle of 400 degrees. So what happens now? How do I think about that? Well, it has exactly the same value as if we hadn't gone a whole turn of 360 degrees. So sine of 400 degrees will be equal to the sine of 400 degrees minus 360, which is equal to sine of 40. And similarly, cosine 400 would be equal to cosine of 40. So they are in pairs. So 400 and 40 are the same. If I went round the clock twice, I would have 720 degrees plus 40. Sine of 760 degrees would be the same as the sine of 760 minus 2 turns, which is 2 lots of 360, which is 720, sine 40. So you can see there's a family of angles here. Sine 40 is the same as sine of 360 plus 40, which is 400. Or sine of 40 is equal to sine of 2 turns, that's 720 plus 40, sine 760, and so on. And I can keep going round in circles like that, but the values return to their, every 360 degrees, they return back to where they started again. So if you have an angle of greater than 360, if you subtract 360 or however many lots of 360 fit, then you will get an equivalent value. Same for cosine. So let's say we had cosine of 1,000. Well, I know that 360 goes into 1,000 twice, 720. So it's going to be the same as cosine 1,000 minus 720, which is equal to cosine of 280. And cosine of 280 lives here in this fourth quadrant, and cos 280 is going to be the same as cosine of 360 minus 280, which is equal to cosine of 80. So there's a whole family of angles there, and you can be going over 360 degrees many times over. You just need to get rid of all the multiples of 360 from that, and you then find its partner angle that sits between 0 and 90 degrees. And we can also have the idea of negative angles. So when I created my angles before, I was looking at them in terms of movement in this positive direction. And this gives me a positive angle. Maybe this is the angle 200 degrees. But I could have got to the same place by working in the other direction. I could have gone that way. And this is a negative angle. And hopefully you can see that if I've gone 200 degrees in an anti-clockwise direction to get to that red radius or line, that's the equivalent of travelling minus 160 degrees. So sine of 200 degrees is the same as the sine of minus 160 degrees. And similarly, cosine 200 is equal to the cosine of minus 160 degrees. They're just two ways of getting to the same location on our unit semicircle. And you can do negative angles that are greater than 360. We could have sine of minus 400 would just be going around the circle, minus 360, and then coming to a halt. There would be the same as sine of minus 40. Because I've been around a whole turn, so I can forget the 360 degrees that I've already been through, because that's returned me back to where I started. So it's equal to sine minus 40. And we know that sine minus 40 is the same as the value of sine of 320, because I'd get to the same place by going in a positive direction. So these are the same value. They're just different ways of expressing the same angle, effectively. And where does the tan ratio come into all of this? Well, we haven't mentioned it so far, but very simply, if you look at the original triangle that we created, so let's just put that back into place there with our two sides. Now 3 sides now in place. We know from our ratio that tan of an angle, tan theta, is equal to the opposite side over the adjacent side, which in this triangle, well, the opposite side is the y coordinate, and the adjacent side is the x-coordinate. But we also know that y is equal to sine theta and x is equal to cos theta. So tan theta is equal to sine theta over cos theta. And what does that do to the value? The equivalent angles for theta are the same as if we were working out the equivalent angles for cosine and sine. But what happens to the values? Well, in this first quadrant, both sine and cosine are positive. So tan, by definition, must be positive in there. But when we go into the second quadrant, because sine is positive there and cosine is negative there, sine divided by cosine would give a negative value there. In the third quadrant, both sine and cosine are negative, so tan would be positive. And in the last quadrant, this time cosine is positive and sine is negative, so tan would be negative in there. So we can see that the values of the tan ratio go positive, negative, positive, negative. So, for example, tan 45 is positive, and that would be equal to the minus tan of 135, because in the second quadrant it's going to be negative, which would be equal to tan of 180 plus 45, which is tan 225 in the third quadrant. And then in the last quadrant, this would be equal to the tan of 360 minus 45, which is 315, but it would be minus because in that quadrant the ratio is negative. It's tricky to get your head around it, but once you've started working with this and working around the unit circle, you will very quickly get the hang of it. So in summary, what do we know? Well, we're going to come on in the next video to actually using this knowledge. It might be a little bit of a so what video so far, but what we do know is in that first quadrant, all three ratios, sine, cosine and tangent, are positive. In the second quadrant, only the sine ratio is positive. In the third quadrant, only the tan ratio is positive. And in the fourth one, only the cosine ratio is positive. So this little ASTC is something that's very important to remember. Find a way of remembering it. All students take CAS. All stations to Cairo. Whatever you need to remember it is very important, because knowing the value of the ratio in each quadrant, whether it's positive or negative, and then being able to use the unit circle to find equivalent angles will be very important at the next step. So we'll stop there, pause there, so that you can get your head around what we've just done. We've thrown a lot of information in there in this video. And in the next video, we'll come on to using that and applying that and seeing how that might be useful to us in some of the problems that we're going to be set on the course. But I hope that you are able to keep up with that. Thank you for watching. Hope you found it useful. Don't forget to like this video and subscribe to my YouTube channel, IB Maths Intense. Tell your friends I'm here. Write me an email at ibmathsintense@gmail.com if you've got any questions, or if there's anything you want me to cover, or if you spotted any mistakes. In the meantime, continue to enjoy your maths, keep in touch and stay healthy.